Okay. Good morning. Thanks for coming. So I'm going to talk about a basic problem in geometry processing, which is you have a surface with a vector field on it, and you want to find a coordinate function that increases uniformly as you travel along the vector field. So for instance, if I draw integer grid lines, they should be orthogonal to the field, and they should be very evenly spaced. Now, why is this a fundamental problem? Well, it shows up all over the place. For instance, it's the basis for a lot of regular meshing algorithms. It's used in various kinds of shading, like this brushed metal or the hatching. And it's also connected to a lot of different natural phenomena, which I'll discuss today. If you want to attack this problem, you first have to come to terms with a mathematical fact of life, which is that you can't always get a perfect solution. In other words, not all vector fields are globally integrable. For instance, even with this very nice vector field on the torus, you might have to sacrifice spacing to get good alignment, or give up entirely on alignment to get perfect spacing. Or there's a very interesting third option, which is that you can get both good spacing and good alignment by giving up a little continuity, or in other words, by allowing singularities in the parameterization. For instance, even the Cactus knows that if you want to get vertical stripes of uniform width, you might have to allow one stripe to branch into two as the trunk gets thicker. And this kind of behavior is what inspires the algorithm I'll talk about today. In the end, we parameterize vector fields by just minimizing a simple convex-quadratic energy, which means we get provably optimal solutions. And that ends up being about 10 times faster than existing methods, because at the end of the day, the main cost is just a single sparse matrix factorization. There are no special conditions on the input, so we can deal with non-integrable or even non-orientable fields. And we also introduce a new interpolation scheme that deals well with singularities and also lets us resolve features well above the resolution of the mesh. So how do you compute a parameterization of a vector field? Well, first you have to choose a representation. And so there are basically two different choices. I could use a real function that directly encodes the coordinate value, or I could use a complex function that indirectly encodes the coordinate as the angle with the real axis, or in other words, the argument of the complex function. Now, with this real function, you notice the value can suddenly jump, which means we also have to deal with integer variables, often leading to difficult non-convex optimization problems. The complex function is continuous by construction, but if it ever goes to zero, then this angle is no longer well defined. And so what people have done in the past is use a fourth order penalty term, which again leads to difficult non-convex problems. So what we'll do instead is forget about this penalty and formulate a problem that's easily solvable by being very careful about the way we treat singularities. So as usual, the basic idea is to minimize an energy that encourages alignment with the given vector field. In particular, if x is the vector field and alpha is the angle of this complex function, then we want alpha to change only as we move along the vector field. Or in other words, if the spatial angular velocity omega is given by the inner product with x, we want the differential of alpha to equal omega. Okay, so what does that mean in terms of our complex function? Well, let's first consider a unit complex function phi equals e to the I alpha. Now, if we differentiate both sides and apply a couple simple transformations, what we see is that the derivative of phi can be expressed in terms of the derivative of alpha. And so if alpha were to change at exactly the prescribed rate, we would see that d phi equals I omega phi. Of course, as I mentioned earlier, this can't always happen. You can't always get an exact solution. And so you have to make some kind of compromise. So what we're going to do, rather than trying to force the vector field to be integrable using curl correction or Hodge decomposition or some other technique, is something very simple. We're just going to minimize the residual of this equation. And right here, something very interesting happens. If you know your differential geometry, you might recognize that d minus I omega is just another connection on the surface. So our whole energy basically becomes something like the norm of the gradient squared, or in other words, the good old-fashioned Dirichlet energy, but with respect to a different metric. And that sounds great because we know how to work with Dirichlet energy, except for one big problem, which is that Dirichlet energy really doesn't mean anything for unit functions or unit vector fields. Because as soon as we have just one singularity, which we're forced to have in general because of the global topology, the energy becomes infinite. And so talking about minimization is now meaningless. And as we mentioned in a previous paper, this can cause some really nasty and counterintuitive behavior in practice. So we're going to take the approach advocated in that paper and define the energy of a unit function as the minimum Dirichlet energy among all possible rescalings. And if we take this idea just a couple steps further, what we discover is that instead of a unit norm constraint at each point, We just want to minimize Dirichlet energy over all functions whose overall, or L2 norm, is equal to 1. And that's very nice because it corresponds to a standard eigenvalue problem. So now we're looking for the ground state of a particular differential operator called the magnetic Schrödinger operator, which I'll talk about a bit more explicitly when we get to the discrete setting. But basically what we're looking for is the lowest energy state of a particle under the influence of a magnetic field. And this is the one and only equation we have to solve to get our parameterization. Now, one more thing you might care about, because it shows up so often in nature, are non-orientable patterns like the stripes on this zebra. But if you look closely at this top example, what you notice is that no matter what kind of vector field we try to put on here, if we try to find a continuous vector field tangent to this pattern, we can't do it. It always flips direction across this middle line. And so we're going to pull a trick from differential topology, first used in the quad cover paper, which is we're basically going to make what's called a branch double cover. So we're basically going to take this disk, make two copies with oppositely oriented vector fields, cut along the discontinuity, and glue them back together to get a vector field that's continuous everywhere on now just still a good old-fashioned two-manifold surface. And so the good thing about this is we can still use that same energy we've been talking about all along. Now, one thing to think about is, even though we have this double cover, we still want coordinates on the original surface. And so we need some kind of compatibility condition on the coordinates we compute on the double cover. In particular, if tau is the sheet interchange map that takes us back and forth between two corresponding points on the double cover, and pi is the projection that takes both of those points back to the original point on the surface, we're going to say that a function psi is conjugate symmetric if composition with tau is the same as complex conjugation. And that condition is going to be enough to ensure that when we take the corresponding angle and plug it into an even periodic function like cosine, we now get a pattern on our surface that's globally continuous, so no seams or jumps. One very important theorem here that we prove in the appendix is that this energy E always has at least one conjugate symmetric minimizer. So basically, we don't lose anything by restricting optimization to conjugate symmetric functions. Okay, so how does this all work in practice? Well, the first thing we need is a domain to work on, and there we're just going to use, as usual, a manifold triangle mesh, and we're going to store the quantities x, psi, and alpha at vertices where angles are encoded relative to some reference edge. And from there are a few details to work through, but the ultimate algorithm just consists of a few simple steps. So first, along each edge, we integrate the angular velocity omega, which we can do by just taking the average inner product between the edge vector and the input vector field. We then build a matrix that looks a lot like the usual cotan-Laplace matrix, except the off-diagonals have these unit complex factors, e to the I omega. And that's our discretization of this magnetic Schrödinger operator. And finally, we compute the principal eigenvector of this matrix using just a simple power method, where the main cost is doing a single matrix factorization. So overall, about the same cost as a standard linear solve. Now, if we want to compute non-orientable patterns, we have to build that same operator on a double cover of our surface. But the very nice thing is that we never have to actually explicitly build this double cover. We can just make a few little local choices on our original mesh data structure to do the same thing. So conceptually, if we have a vertex on our surface, that corresponds to two vertices on the double cover, and we're going to assign vectors that have opposite orientation to those two vertices, making a completely arbitrary point a choice of which vector goes where. Then for each edge on our surface, we're going to connect up two edges on the double cover by connecting the vertex pairs where the vector differs as little as possible. So here the bottom two and the top two. And then finally, by the time we've added a third neighbor, it looks like we just have two copies of our original triangle, so what's the big deal? Well, I've drawn kind of the simplest case here. So for instance, we could have picked the opposite orientation on one of these vertices, in which case we get two different triangles, but still we get two triangles on the double cover for one triangle on the base. Now, a more interesting case is when we have three vectors on the original surface, such that no matter how we assign them orientations on the double cover, when we try to connect up edges such that the vectors are as close as possible, we get a hexagon on the double cover rather than two triangles. And that corresponds to a branch point in the double cover. So overall, they're actually just two simple cases. Either we have an even number of flips as we go around a triangle, in which case we get two triangles on the double cover corresponding to a regular point in the field, or we have an odd number of flips, in which case we get a single hexagon corresponding to a branch point. And for simplicity, we're just going to omit these hexagons from our energy. Now again, it's important to remember we're not ever actually building this double cover. This is just kind of a mental model we're using to better understand and simplify our algorithm. And another nice simplifying assumption we can use here is this conjugate symmetry. So remember I said for each point on our surface, the two corresponding solution values on the double cover are the same up to complex conjugation. So in practice, we're just going to store one of these two values. And when we go to build our matrices, multiplication with any complex value z equals a plus bi is going to be encoded by this little 2 by 2 real matrix. And conjugation followed by multiplication will be encoded by the same matrix, except that we've effectively flipped the imaginary component. Okay, so once we have our eigenfunction psi, we still need to interpret it to come up with a continuous pattern on our surface. And so remember we said our coordinate function alpha can be thought of as the angle of this complex function. So you might think, okay, we'll just take the argument of that complex value at each point and use linear interpolation. The problem is there's some ambiguity here because we can add integer multiples of 2 pi to this angle without affecting the complex value. And in practice, this is going to cause some nasty numerical artifacts. So what we do instead is along each edge, we measure the smallest difference between the angle we wanted and the angle we actually achieved. We call that delta. And then we define what we call the spinning form sigma, which is the angular displacement closest to our target angular displacement that explains the values we actually achieved. And so then if we increment the angles around the boundary of the triangle using the spinning form, we get a different set of coordinates that capture this possible spinning of the angle. So on the left, we see what we get with just the argument. We get all this kind of nasty aliasing. And on the right, if we use the spinning form, we nicely resolve things into these fine grid lines. The same setup is going to help us interpolate the solution near singularities. So remember that we're not forcing the function to have unit norm at each point, which means that wherever it vanishes, the angle is no longer well defined. So what we're going to do is draw a function that looks a lot like the complex argument near 0, except it's also going to be linear along the boundary of the triangle, because that way it can connect up seamlessly with the solution on the rest of the domain. And for this, we have a closed form function that we just subtract from the usual piecewise linear coordinates. So here on the left, we see if we just use linear interpolation, we get all this discontinuity. On the right, if we use this closed form function, we get this nice continuous branching pattern. Finally, we have these hexagons on the double cover where we didn't explicitly compute a solution, but here we can also use our spinning form to get a nice interpolating function. So basically what we do is we split the triangle into 3, we integrate the spinning form along the boundary, and just use an intermediate value at the middle. And so you can see on the bunny, if you look at the tip of the nose, we have this triangle which has been split into 3 pieces. We get this nice continuous function. And the really cool thing is it's even continuous if we have zeros next to branch points. So really continuous over the whole surface. Okay, so let's see how this works out in practice. First, just a simple test showing that the eigenvector problem really is a lot more efficient to solve than one of these non-convex problems. In particular, it's about 10 times faster than this penalty method, and it's going to be about 20 times faster than the mixed integer solver. Here's an example demonstrating the kind of optimality we get from this method. So as the radius of this wedding cake goes from 2 to 3, you notice that exactly every other stripe on level 2 branches into 2. So overall, 2 stripes into 3. Here's a test of robustness. So we add all sorts of noise and holes and other crazy stuff to the mesh, and you can see we still have no trouble computing a nice stripe pattern. And finally, some applications. So one very natural thing to do is to pre-compute a stripe pattern and plug it into a real-time hatching shader so that you don't have to trace out integral curves. Actually, we don't have to have uniform spacing everywhere. So if we multiply our input vector field by some scaling function, either something continuous like on the left or discontinuous on the right, then the algorithm automatically inserts singularities exactly where they're needed to adjust the spacing. And this is something you're really not going to get using an algorithm that's based on angles or unit vectors. In fact, we can deal with completely arbitrary inputs. So here on the left, we have both variable spacing and variable direction, and you can see that without any kind of preprocessing, the output of the algorithm very closely matches the input or the intent of the user. Here's one nice example where we try to mimic the behavior of fingerprints by just plopping down a couple singularities and letting the algorithms handle the rest of the job. Here's one very interesting example where we take a constant vector field and we just perturb it by a little bit of noise. And the result we get looks strikingly similar to Aeolian wind ripples, so basically patterns of sand in the desert. Of course, if you spend enough time in the desert, you eventually run into a cactus. And here what we're doing is we're actually computing two separate orthogonal stripe patterns, so one horizontal and one vertical, and then combining them to get a 2D parameterization, which we use to drive a texture and a displacement map. Likewise, if you've ever eaten a cob of corn, you might notice that the number of kernels increases and decreases as the width shrinks and grows. And so now we can do this on any surface, including this armadillo, which is all ready to eat or be eaten. I'm not really sure which one. And there are some other fun examples in the paper. One final thing we can do, because the algorithm is so fast, is we can create animated patterns by just continuously varying the input vector field. And the motion of these singularities that you see here is known in material science as something called edge dislocation dynamics. So it's very closely related to phenomena at the atomic scale like plasticity. Okay. So overall, what we did here today is really looked at in depth one particular way of dealing with non-integrability in the parameterization problem, in particular sacrificing a little bit of continuity to get better spacing and alignment. And while this might not be the best solution for everybody all the time, I think it's one direction that's kind of been overlooked and is really worth thinking about more, especially if you can trade it off continuously with these other approaches to dealing with integrability. In the paper, we have some very detailed pseudocode explaining how all this works, and on the web, we also have some actual code that not only does parameterization, but also optimal field generation and singularity editing, and I'll give you a very, very brief demo right now. So here's our surface, and I hit the space bar, and all of a sudden we get our stripe parameterization, and it's very fast, so we can easily edit the singularities, and we can also adjust in real time the spacing. And one thing you notice, I'll draw the wireframe here, is, again, we can really get features far above the resolution of the mesh with no problem. The other thing that's interesting here is that the number of singularities really has to do with how fine these lines are. And as we add more and more singularities, we get closer and closer to our original field. Okay. So one thing that some people might be wondering about is, do these insights apply to quad meshing? And the answer is, yeah, they definitely seem to help out there as well. But we're still working through a lot of the details there, so stay tuned for more. And thank you for your attention.
Thank you very much. So we have time for questions. Please come up to the mics if you have any, and state your name and affiliation. So I do have a quick question to start with.
Okay.
Or maybe not that quick. So I was wondering whether, when I look at the intersection of two of these stripe patterns, right, it looks like if you could address one of the cells which is formed by this intersection, you could pick a color here and you could use this for general purpose texturing, right? So that you would have, it's like a grid which varies in resolution across the surface.
Yeah, so that's kind of what we did with this cactus and corn example.
Okay.
Yeah.
Even though, so the question is, can you count the lines? If I give you a point on the surface, can you know, like, this is in between this line and this line somehow?
Can you kind of index them?
Yeah, sort of a global index on the surface.
Yeah, so you can kind of assemble these in 2D so that you get a parameterization that is continuous except at some cut graph. I mean, we don't actually have to compute a cut graph, but this is what will happen if you try to assemble these in the plane. And so this gives you some kind of global indexing, but like any parameterization, you know, there's some place where these indices have to jump.
Okay, sure, yeah. But I think that would be addressable somehow. Okay, interesting. Yes, please.
Yes, this is Leo Gibas from Stanford, and very nice work, Keenan.
Thanks.
Just a quick question. In the stripe pattern you generated on the wedding cake, I was a bit surprised that the new stripes started in the middle of the vertical wall and not at the edges. This doesn't make sense to me. How come this happened?
Right. So the location of the singularities actually doesn't have to do with the extrinsic curvature of the surface. It has to do with the curvature of the connection, which in this case kind of has to do with the curl of the input field. So there's no particular reason they have to show up where the actual geometry bends. But that's something you could try to incorporate into the energy or the field.
Thank you.
Please.
Hi, Nina Menta, UC Davis. I was wondering if you wanted to say a few words about why the turning such a stripe pattern into a quad mesh is not obvious?
Things that people care about a lot in quad meshing, like boundary conditions, handling sharp features, those kinds of things are things we haven't really touched on yet. So we're thinking about those right now.
Okay, thank you very much.